I'll try to get like a practice little test out to you guys on Friday. Okay, I'm still writing the actual little test. So as soon as that's done, I'll get out a practice one. Any questions about that stuff coming up? Okay, and then also, like I said, one sheet of notes. You can use front and back. You can use the sides of the paper if you want. You can write in as small font as you want. It doesn't matter. Okay, so last time, just to remind you, we covered the Kkt conditions, which were a set of conditions that we thought about applying to a general problem of this form. And they're a set of 4 conditions. The first is stationarity. Okay, I have another, it's annoying, I'm sorry, I have another bug in my stationarity notes. Let me just pull up the actual Kkt conditions lecture to show you the actual condition. Don't want to print it. It's supposed to be this guy. Okay, so it's of course equivalent to what I wrote down last lecture and what I had in the review slide just now when these are convex, but in general it's not. So what this is saying is that if I take the Lagrangian, this is the Lagrangian corresponding to that problem, and I treat it as a function of x with u and v fixed, then the current x I'm looking at must minimize the Lagrangian. Because I've already taken a subgradient of the Lagrangian. This is meant to be interpreted with respect to x, this subgradient, then that contains 0 at the point x. So x minimizes the Lagrangian over all possible values of x. If we look at the Lagrangian as defined by the fixed pair uv. That's what the stationarity condition says. And I had it in the review slides in this form, which was a bug I've had in these slides for a little while. This is only equivalent to that when f, h, and l are all convex. Okay, otherwise, our rule about taking subgradients of sums and sums of subgradients, those things aren't the same if f and hi and lj, if some of them are non-convex, for example. Okay, the complementary slackness condition said that the dual variables that we're looking at, they have to either be 0 or the constraints, the ith constraint function, around which this dual variable is defined has to be tight. So I either have to see an inequality here at hi or ui has to be 0. That's complementary slackness. And then the last two are just feasibility. X must be feasible for the primal problem and uv must be feasible for the dual problem, but that just is a condition on u. So if these 4 conditions hold, then we saw that, well, that's actually always sufficient for implying optimality. So if you can satisfy these 4 conditions, okay, then what we proved is actually the duality gap is 0, which means that x must be primal optimal and uv must be dual optimal. And in kind of the other direction, we showed that under 0 duality gap between the primal and the dual problems, if we knew that there's a 0 duality gap, say, for example, if this problem was convex and strictly feasible, then we know by Slater's condition that there's going to be 0 duality gap, then any solution must satisfy the Kkt conditions. Okay, so they're actually necessary in that situation. So the way that you can think about it, I think that the easiest way to remember it is that if you have a convex problem for which the problem is strictly feasible, then these things are equivalent to finding optimal dual and primal solutions. And in that case, actually, there's no bug in the way the stationarity condition is written, because for convex functions, that's fine. Okay? Those are the Kkt conditions. Any questions about them? Because they're going to, duality and the Kkt conditions are very intimately tied, so I think it's important to clear up any confusion about this before we go on. Okay, good. So we're going to talk about uses of duality today and what I'm calling duality correspondences, so things that relate very closely to duality, like conjugate functions. And 2 kind of key uses of duality that we've already somehow pointed out but maybe haven't explicitly said as uses are the following. I guess this one we actually did talk about a little bit. So for any x that's primal feasible and uv that's dual feasible, this quantity, the primal criterion minus the dual criterion, we call this the duality gap between x and uv. So first thing, notice that this thing is always non-negative, right? Because by construction, for any feasible x and primal feasible x and dual feasible uv, this function g has to be smaller than this function f. Right? So this thing is always larger or equal to 0. And in fact, it upper bounds, say, the difference between f at x and f at x star. Okay, this just comes from the very simple fact that GUV, right, lower bounds the primal criterion optimal value for any dual feasible u and v by construction. So, the signs get flipped when we take their negatives. And if we just add f of x to each side, we get that the duality gap, right, is bigger than or equal to f of x minus f star. So we call this the duality gap. Which is very useful, right? Because let's suppose that we are running an algorithm to optimize the primal problem, and this algorithm produces dual iterates along the way. Interior point methods will do that, for example. Okay, but you could actually think about maybe simultaneously running an algorithm on the primal and the dual, or some algorithms actually operate on the primal and the dual kind of explicitly like interior point methods. And we'll learn kind of more about dual-based algorithms towards the end of the course. So suppose you have like iterates uv and iterates x, and you're trying to march down the primal criterion, you're trying to march up the dual criterion to maximize the dual and minimize the primal. Then at any point you can look at this gap. This is the duality gap, and that'll tell you, for example, how far you are currently from primal optimality and how far you are currently from dual optimality. Okay, so this upper bounds both f of x minus f star. It also upper bounds g star minus guv. Okay, by essentially the same arguments. So it gives you an upper bound on, either how far the primal iterate you're looking at is from optimality or the dual iterate. Okay, and also when this thing is 0, this implies that we must have optimal solutions, right? Because then, for example, when this is 0, it implies that, for example, f of x is equal to f star and guv is equal to g star. That's something that we used kind of in a very important way when we talked about the Kkt conditions. But this can be practical too, as we said, for algorithms. Another use of duality, which is, I think, in many ways, the most important aspect of deriving a dual problem, is not usually to upper bound or lower bound the criterion value, but actually to characterize something like the primal solution in terms of the dual solution. Because it may be the case that when you derive the dual is actually easier to solve than the primal. So once you find its solution, oftentimes, let's say, you can actually express the primal solution in terms of that. Okay, and that's often, I think, or in many cases, the most useful way to think about duality is it provides you with another lens for trying to solve, another way to try to solve your problem. Okay, and this actually comes from the stationarity condition of the Kkt conditions. So if we look at a situation in which strong duality holds, then we know that any primal solution must satisfy the stationarity condition, right? Any primal and dual solutions must satisfy the stationarity condition, which means that if you happen to find u star and v star, if you derived the dual, you solved the dual, you got u star and v star, and you wanted to characterize the primal, then you could think about how to minimize the Lagrangian over all x at the value of u and v star that you found. If you could do that, that would give you a primal solution. Okay, that's just invoking essentially the stationarity condition from the Kkt conditions. And if this solution was, if the minimizer here was unique, it would tell you the primal solution. If it wasn't unique, you can use it to kind of characterize the set of primal solutions, for example. So let's just dive into a bit more detail. Consequence of stationarity for the Kkt conditions is that under strong duality, right? Under strong duality, in which case we know that the Kkt conditions and having solutions are equivalent. If we have any dual solution, then any primal solution must minimize the Lagrangian, right? Defined around u star and v star. So because this doesn't have constraints, oftentimes we can express minimizers of the Lagrangian in somewhat closed form. In fact, that's how we would usually derive dual problems in the first place, by looking something like this. So if you're solving the dual, you're usually in a situation in which you can, and if you solve the dual and you've gotten to the dual, you're usually in a situation in which you can minimize this thing in unconstrained form without kind of any problems, right? You can either characterize or write down the solution here explicitly. And if the solution to this problem is unique, then it must be the primal solution, right? If the solution to this is unique, then it must be the primal solution. And otherwise, we can think about it as, say, characterizing the primal solution. And this is going to be very helpful when the dual is easier to solve than the primal. Okay. So one thing to keep in mind, for example, is that if your problem has a lot of variables but few constraints, then it may be a good idea to derive the dual, right? Because then the dual problem will have few variables, because the dual problem has the number of variables equal to the number of primal constraints. So it may be easier to solve than the primal. So here's an example of that. Exactly. So this is a nice example that from the Boyd and Vandenberg textbook. So let's suppose we wanted to minimize a criterion that's of the form sum of fi xi. Okay, if we didn't have this constraint, then this would be very easy because we can minimize out over every xi individually, right? Let's suppose xi was actually a single variable. We just would perform n univariate minimizations. Doesn't matter really what these functions are. Univariate minimization, as I've claimed before, is kind of always easy, right? We can just plot the function and lay down a grid of points and find a point that's close to the minimum, do some kind of bisection search. But in any case, it would be certainly easier to solve each of these problems individually than it would be to solve the whole thing if this depended on kind of all of x. But unfortunately, this constraint is complicating, right? Because this constraint ties together all of the variables. So here I'm imposing the constraint that I must have, let's say, A transpose x equal to b. No longer does it decompose into kind of n separate minimization problems. So something nice happens when we look at the dual. And this is actually kind of a preview of something called dual decomposition that we'll talk about towards the end of the course when we talk about operator splitting techniques. So there's kind of a much broader class of examples in which you can use arguments, like this. So this is not just somehow a coincidence. It's a preview of dual decomposition. But the idea is that we're going to derive the dual function, and the dual function is going to separate into, actually here it's going to be very simple because it's going to be, it's just going to be involving one variable, right? If we had actually many constraints here, many equality constraints, then we would still see something nice in the dual. That's called dual decomposition. Let's suppose that each of these functions is smooth and strictly convex. Okay, so just for simplicity for now. And let's write the dual function, right? The dual function is gotten by minimizing the Lagrangian. What is the Lagrangian? It's the criterion plus, I'm calling the dual variable here v. V times b minus A transpose x. Okay, and I've just pulled out b times v because that doesn't depend on x, so the minimization is not affected by that. And let's look at now what we're doing. We're minimizing over all x the sum of fi xi minus v times A transpose b. V is the scalar, it's our dual variable. That's the same thing as minimizing fi of x I minus v times the sum of ai. Wait, that's not supposed to be b. I'm sorry, it's supposed to be x. A transpose x. ai xi. Okay, and the nice thing here is that this minimization separates into n separate minimizations. So this is just a minimum over, say, xi, fi xi minus v times ai xi. Okay, so that's kind of the piece of the Lagrangian we have to figure out. This is the piece of the dual function we have to figure out. Right, minimizing over x gives us the dual function. So let's just call this whole thing. This may seem kind of foreign for now. We're just going to call this whole thing minus fi star of ai times v. Okay, this may look like notation for now, but what we're going to learn actually, kind of maybe a quarter of the way through this lecture, is that this is called the conjugate function. Rather, the conjugate function is defined by a max, so I've used a negative sign, of fi. And it's often something that we can explicitly compute, especially in conditions like this, smooth and strictly convex. That's why I wrote that down. Okay, so this is something we can call just the conjugate function of fi. Okay, but it's just a function, some function of v after we've minimized out over xi, and it's also, in principle, could be simple to write down because this is just a function of one variable. So the dual function, then the whole dual function becomes, as I've written down here, bv minus the sum of fi star times of the argument ai times v. Okay, and this is just a function. The dual problem now is just a function of is an optimization problem involving one variable, right, v. And we can write this dual problem equivalently if we wanted to, say, as a minimization problem just by flipping the sign here. And one property of the conjugate function that we'll learn is that it's always a convex function. I mean, we kind of already know this should be a convex problem because it's a dual problem, right? But it's just kind of reinforcing that idea. So this is a convex problem. It's a dual problem. It involves one scalar variable, so it's much easier to solve than the primal, right? We just, like I said, for example, plot this over all values of v that you can afford to, and then do like bisection search or something. So once we've solved that, we got the dual solution v star. We know that the primal solution must minimize the Lagrangian over all x at v star. Right, so we go back to the Lagrangian, and we think about what it means to minimize the Lagrangian, right, this guy, over all x at v star, or let's say this guy, which is equivalent. So this doesn't depend on x, so we're thinking about minimizing out over x. It's actually have to just solve this problem for each I. That's going to characterize for us xi. So for each component of the primal solution, we ask ourselves, what value of xi minimizes this after I plug in v star? And because fi was smooth and strictly convex, I also used that as a simplifying assumption here, so we could just take the gradient of this and set it equal to 0. Okay, so we basically take the gradient, set it equal to 0. Set it equal to 0, which has the gradient being equal to, say, ai times v star. In fact, this is just the derivative of fi with respect to xi, right? Because I said it's a scalar variable. So this notation is kind of overloaded. And this defines us the primal solution in the component xi. Okay, so this is a case in which primal optimization problem had n variables, hard to solve. Dual problem had one variable, very easy to solve in principle. Then we recover the primal solution by just solving this equation given the dual solution. Okay, that's just maybe a general form example. Any questions about that? Okay, I think our examples will get more clear as we kind of consider more specific instances of these functions too. So you'll see some nice specific instances in the lecture today. So today's lecture is going to be covering the following topics. So we'll talk a bit more about dual norms. We've kind of touched on them from time to time across various lectures. We'll introduce conjugate functions and talk about properties of conjugates. And once you learn conjugate functions, I think deriving duals is going to be way easier. So right now, deriving the dual is, it's maybe kind of a chore. You write on Lagrangian, then you think about minimizing each piece. Once you learn conjugates, I think it's going to simplify the way you approach deriving duals dramatically. At least I think it does for most people. Then we'll learn about dual cones. And if we have time, I'll talk about some kind of subtleties of duals and some tricks that you might need to be aware of in deriving duals. And there's a ton of related stuff I could talk about. In previous years' courses, I've kind of gone off the deep end and talked about duality for a long time. So if you're curious, you can look at notes from like 3 or 4 years ago. There's lots of neat connections to all different areas involving duality. So let's talk about dual norms. So we've defined them in previous classes, but we can think about them now kind of as being tied to duality. So let's think about an arbitrary norm, right? And good examples of norms are, say, like the LP norm on vectors or the trace norm on matrices. So these are two norms that we've seen being used in various optimization problems that we care about. Remember that we defined its dual norm as the maximum inner product we could achieve with x over all vectors that have norm less than or equal to 1. So the dual norm at a point x is the maximum inner product that we can achieve with x over all vectors that have norm less than or equal to 1. Okay? That's the definition of the dual norm. So this gives us an equality that goes by different names. So when this is the L2 norm, it goes by the Cauchy-Schwarz inequality. When this is the LP norm, if we look at an LP norm, this inequality is often referred to as Holder's inequality. But it's, you can just think of it as the dual norm inequality. It holds for any pair of norms that are duals. And it's very, it's kind of obvious why this holds. So we can equivalently write the dual norm in terms of an absolute value, right? The dual norm at x, that's how we denote it. It's the max over all z whose norm is less than or equal to 1 of, let's say, the absolute value of z transpose x. That's also true. Why? It's because if z has norm less than 1, then so does minus z. Right? So we're already considering both z and minus z in this inner product, which means that we can write the absolute value. And now let's consider, for example, you give me an arbitrary vector y. I'll call it y so we don't confuse it with this max. And I'll look at the vector y over its norm. And I'll call that z. So this thing has norm 1, right? Then the norm of z is 1 by construction. And by definition, we know that z transpose x is less than or equal to the maximum over all possible z's that have norm 1 of the absolute value of z transpose x, which is equal to the dual norm. Okay, but now if I just remember that z was y over its norm, this tells me that y transpose x is less than or equal to the norm of y times the dual norm of x. Okay, so that's how we prove that inequality. So that inequality is used very often. It's very useful. And if we go back to our examples, remember that we stated previous times in the course, just as a fact, that the dual of the LP norm is the LQ norm, where 1 and p are sometimes called complementary. 1 over p plus 1 over q is equal to 1. So this gives us stuff like the 2 norm is its own dual, and the 1 norm is the dual of the infinity norm, and vice versa. And another important and useful fact is that the dual of the trace norm is the operator norm. Okay, you can actually think of this as being very analogous to the 1 norm and the infinity norm being duals, because this is kind of like the 1 norm for matrices, right? We're summing up the singular values. This is kind of like the infinity norm for matrices. We're taking the biggest singular value. So this relationship is really analogous to the duality of the L1 and L infinity norms. Okay, you can show that the dual of the dual norm is the original norm. Okay, so that means that once I tell you the L1 norm's dual is the L infinity norm, that means that the L infinity norm's dual has to be the L1 norm again. Right? If I take the dual twice, I have to get back where I started. And we can actually prove that using duality. Okay, so we're going to do that just now, this fact. The dual of the dual norm is the original norm. We're going to prove that using duality. And in fact, you can tie a lot of what I said here to duality. So I just picked kind of one thing to tie to duality, and that was this fact. So let's consider the absolutely trivial problem up there. Minimize overall y. The norm of y subject to y equals x. X is fixed. It's not an optimization variable. It's fixed. It's just a vector you give me ahead of time. Okay, what's the optimal criterion value in that problem? Just the norm of x, right? There's only one feasible point. The minimum is therefore just the norm of that point, norm of x. But I wrote it this way so I could derive a dual. And this is actually foreshadowing something that we'll do often when we try to derive duals of unconstrained problems. Okay, we introduce constraints so we can actually get something useful out of it. So the optimal value of this is just the norm of x, right? The Lagrangian is just the criterion plus a dual variable u transpose times x minus y. Okay, which I'm just writing as the norm of y minus y transpose u plus x transpose u. So now I want to minimize the Lagrangian over all y to get the dual function, right? That's what I am going to be doing. Remember, x is fixed here. Y is my primal variable. That's how I define the dual function. So there's kind of two cases we have to think about. Okay, the first case is when the dual norm of u is bigger than 1, and the second case is the dual norm of u is less than or equal to 1. So, actually out of paper. Okay, it's going to have to serve as our substitute paper for now. So let's think about two cases. The first is when the dual norm of u is, let's say, less than or equal to 1. Maybe the easier case. Okay? Then let's look at the, let's say, the maximum over all y of y transpose u minus, we have the norm of y, right? And put a minus sign out front. That's the same thing as what we have here. Right here we have the minimum over all y of the norm of y minus y transpose u. I just flipped the signs and I've used max. So if the dual norm of u is less than or equal to 1, then we know that actually this guy, right? So let's just think about this maximization problem. Y transpose u is always less than or equal to the norm of y times the dual norm of u. That was from that dual norm inequality. But that thing is just less than or equal to the norm of y. Right? Because I told you the dual norm of u is less than or equal to 1, which means that this max can only ever, this max is equal to 0. Right? Because I can make it 0, say, at y equals 0, and this thing is always less than or equal to 0. So the biggest this can be is 0. Okay, so we get this. So that means that if the dual norm of u is less than or equal to 1, then when we minimize the Lagrangian over all y, that term, norm of y minus y transpose u, that minimum value is 0, and we only have x transpose u in the criterion. Okay, how about the case when the dual norm of u is, let's say, bigger than 1? Then let's look at, I'm just going to get rid of the minus sign here. Maybe it's unnecessary to have it around. So the maximum over all u of y transpose u minus the norm of y. Okay, what do you guys think that's going to be if the dual norm of u is bigger than 1? It's going to be infinite, actually. And the reason is because we can always find, let's say z with norm z equals 1, such that z transpose u is equal to the dual norm of u. Okay, we can always find this being true. And let's take, this is because, right, this is saying that we can always just pick a z that achieves the max here. That's going to be the z that achieves the max. That's always true, regardless of how big this is. We're just saying this is the z that achieves the max, right? That's just looking at the guy that is the argmax over all z less than or equal to 1 of z transpose u. And now let's take, for example, y to be equal to t times z for some t that's positive. Then, in fact, y transpose u is going to be equal to t times the norm of u, dual norm of u, right? Because the norm of y is going to be equal to t, and so that just comes from, for example, taking multiplying both sides of this equation by t. Yeah, this is what we know. But now look, I have y transpose u for this y being equal to t times the dual norm of u, and I'm subtracting off the norm of y. So for this y, right, I have y transpose u minus the norm of y is equal to t times the dual norm of u minus t. And that's going to go to infinity as I send t to infinity, because the dual norm of u is strictly larger than 1. So in this case, the dual norm of u is bigger than 1, then I can maximize this away to infinity. So therefore, the dual function in our case, right, which was actually the minimum over all y of the Lagrangian. We can think of it as being x transpose u minus the indicator that the dual norm of u is less than or equal to 1. Right? When this is true, it contributes 0 to the criterion. When it's not true, it contributes negative infinity to the criterion. Right? Because we're actually considering the min in the problem here. Okay. So that's the dual criterion, and the dual problem is, of course, to maximize this. So the dual problem is max over all u of g of u, which is the same as maximizing over all u with dual norm less than or equal to 1, x transpose u. Right, because I've taken this indicator and I put it as a constraint in my problem now. It's a trick we've done several times before. Okay, so that's the dual. The primal is up there. What we know about the primal is that actually it's convex, because norms are convex, and it's strictly feasible because we actually have no inequalities. Right? So strictly feasible means we can find a point that satisfies all of the equalities, and it satisfies the inequalities strictly, but there are no inequalities, so that's fine. So Slater's condition tells us that actually these two things have the same criterion values. F star is equal to G star. But F star, remember, was just the norm of x. This is a trivial problem. And G star, what is this? This is exactly, by definition, the dual norm of the dual norm at x. Right? This is how we would define this is how we define x star star, exactly by this equation. So by strong duality, the criterion values matching implies that these norms are actually the same. Okay, the norm of x is equal to the dual of the dual norm of x. Okay, there's lots of connections you can make between dual problems like this and dual norms, and we'll see a bunch more today in terms of how a norm in the primal kind of corresponds to a term in the dual. Okay, so just moving forward, a really kind of important definition for us is going to be the conjugate function. And I think that it's going to make deriving duals much more formulaic once you see the... Oh, yeah, question?
To the previous slide, what was the motivation for considering that trivial-looking problem? Like, what's the thought process behind coming up with, starting from that problem?
Yeah, that's a good question. So first of all, I'm going to kind of claim that when we have unconstrained problems, you'll see several examples in this lecture. We introduce constraints in order to derive dual problems. Because we don't have any dual variables for an unconstrained problem, so there's nothing we can do. Right? In a sense, it's just a vacuous exercise to try to drive a dual of an unconstrained problem without introducing constraints. So I had that in mind kind of going into this, that this is a common thing we do. And I guess we wanted to start off with a problem somehow that by invoking strong duality would give us the conclusion we wanted to. Right? So we wanted to have a problem whose optimal criterion value was the norm of x, and this is kind of somehow the simplest problem I could think of, whose optimal criterion value is the norm of x. There may be other ways to derive this equivalence as well. But other problems, other questions? Okay, good question. So the conjugate function is defined given a function f. We define its conjugate, which we denote by f star, by the following equation. So at a point y, f star at y is defined as the maximum inner product we can achieve with y after we subtract off f. So it's the maximum over all x of y transpose x minus f of x. Yeah, that's the conjugate function at y. And okay, not to confuse notation too much, I'm actually, you can see, this is the star. It's a asterisk. It's not a star. So that is supposed to be the conjugate function, and that's supposed to be the optimal criterion value. So I've tried to be careful with that in all the problems on the homeworks, or I think we've tried to be careful about that. But Sometimes we may mix it up. But that's the notation that I think is most common. So F star for the optimal criterion value and F asterisk for the conjugate. But I will just call that F star because I don't like to say F asterisk. So OK, that's the conjugate. And what's one thing that's nice about the conjugate function is that it's always convex. This is, in fact, somehow the same property as dual problems always being convex. And you'll see why I'm saying it's the same property in just a moment, because conjugates are so closely tied to duality. So it's always convex even if f was not a convex function. Okay, it's kind of this crazy property. It's like we have this crazy property of duals. And why is that? Well, as a function of y, right, each of these things is just affine. So they're convex functions of y. Fix x. As a function of y, this is affine. Then I'm taking a maximum over affine functions, right, which are convex functions. So the maximum of convex functions is convex. And that's why this is a convex function of y. Okay, and here's like some nice kind of graphical depiction from the Boyd and Vandenberg textbook. You can think about this geometrically in terms of sets as well, or you can think about this in terms of the graph of the function. Personally, I don't really remember these kind of pictures when I think about conjugate functions, but maybe they help for some people. At a point y, I think about the largest inner product I can attain with y. So this is just one dimensional. So this is just the biggest value of xy minus f of x. So after I take this line and I subtract off my function, I look at the biggest value that I can attain, and it happens to be here in the picture. And that's how we define the conjugate at the point y. Okay, and just another connection is that when f is differentiable, conjugation is also called the Legendre transform. If you're taking a physics class, or maybe some classes in engineering use this as well. If f is differentiable, this is just called the Legendre transform of f. It's the same thing. So there's a bunch of really nice properties of conjugates. Here they are. I don't think, well, let's just like say prove the first one. The rest you can prove in ways that were similar to, for example, what I did here with the dual norm to prove this property, or similar arguments to things you've seen so far. And maybe even one of these is a homework question. I can't remember. So I won't venture down here. We'll state them, but I'll prove this. We'll prove this one together. Okay, so this thing is called Fenchel's inequality. It's the first property of conjugate functions. And it's that for any point x and y, f of x plus f of y star, sorry, f of x plus f star of y is bigger than or equal to x transpose y. That's true for any points x and y. Where does that come from? Well, let's just write let's just write this as, by rearranging, that's just the same thing as saying that f star of y is bigger than or equal to x transpose y minus f of x. Right, but now when you write like that, this is obvious because by definition, this is the maximum, let's say over all points z of x transpose z. No, that's wrong completely. This is the maximum over all points, let's say z of z transpose y minus f of z. So we define the conjugate function. Right? So clearly, the max is going to be bigger than just what this looks like at one point, say x. So that's Fenchel's inequality. Okay, it's useful in, I think, many situations. For example, I don't know if we have this here. Yeah, we'll think about what this implies for certain function conjugate pairs in just a second. A property similar to, let's say, the dual of the dual is the primal norm, is the original norm. We have that the conjugate of the conjugative function is the function itself, but that's only true when f is closed and convex. So it's not true for arbitrary functions. So how do you know this can't be true for non-convex functions in general? What's one thing that's stopping this being true for non-convex functions in general? So, yeah.
So the dual will be convex and take dual convex.
Right. So this thing has to be convex by this property we said here, and the right-hand side can't be anything. So this definitely can't be true in general, but it is true for convex functions, and it's true for functions that are closed and convex. Closed is a very, let's say, a very minor additional assumption besides convex. So for example, functions that are continuous are everywhere are closed. A function is continuous in all of Rn, it's closed. Closed formally means that the function has closed sublevel sets. Okay, so that's the definition of it, but almost all functions you'll look at are closed. So for a function that's closed and convex, then this property is true. Conjugate of the conjugate is the original function. And in fact, this is something you can prove using arguments similar to, let's say, the things we've seen so far. In general, it's always the case that the conjugate of the conjugate is less than or equal to your original function. This is true everywhere for all arguments, even when it's not closed and convex. Okay, there's this very nice relationship between conjugates and subgradients that we're going to have you prove on the homework, I think, and then we're going to invoke it when we talk about dual algorithms in the advanced lectures towards the end of the course. And that is as follows. It looks like kind of a notational swap, but it's actually a very important property. If you look at the subdifferential of your function f at a point x, and y is in the subdifferential, so if y is a subgradient of your original function f at the point x, that is equivalent to x being a subgradient of f star at y. Okay, so switch the roles of y and x and change the function to its conjugate. It's an equivalence for subgradients. And actually, both of those properties are equivalent to having an equality in Fenchell's inequality. Okay, having x transpose y being somehow the biggest it can possibly be, equal to f of x star plus f star of y. Okay, so that one we'll hold off on describing why it's true, because I think it's on your homework. And then this last property just shows you that conjugates are additive if you have functions over blocks of variables. So, if I wanted to derive the conjugate of this function, then it's just the conjugate of f1 plus the conjugate of f2. So let's go through some examples. How about a strictly convex quadratic function? So let's look at this thing. So let's think about this function, x transpose qx, where q is positive definite. Strictly convex quadratic function. And let's derive its conjugate. So remember, f star of y is the maximum over all x, y transpose x minus the function. So 1/2 x transpose qx. Okay, and I can write that maybe just because we're generally more comfortable with minimizations than maximizations, in terms of deriving things, as minus the minimum 1/2 x transpose qx minus y transpose x. Okay, it's the same thing. So what's the minimizer here? See if my my little mnemonic or whatever worked from a few lectures ago. This should be, I think, immediate for quadratic functions. So remember I said if you have a quadratic ax squared plus bx plus c, the minimizer is minus b over 2a. So what is it going to be here? The minimizer is q inverse y, right? Because it's think about it like this. I have to take b, which is y, and divide by 2a, but a is a matrix, so 2 times a half q is q, so it's just q inverse y. Okay, or you could take the gradient here and set it equal to 0 as well. That would have been fine, but for quadratics, I somehow just always remember this rule. I think it's helpful. Okay, and so then what's the minimum value? It's what happens when I plug that in, right? So I'll get minus 1/2 y transpose q inverse q inverse y plus y transpose q inverse y. So I moved the minus sign through, and I plugged in for this value, right? And that's just equal to it's just equal to, of course, it has to be convex, right? So we kind of know that this has to be a convex quadratic. Y transpose q inverse y, right? We had one copy and we had negative 1/2 copies of the same quantity. So the conjugate function of, let's say, this quadratic form is another quadratic form where I've just replaced q by its inverse. So it's maybe not a very surprising relationship once we've derived it. Fenchel's inequality then, this is kind of interesting. Fenchel's inequality, what does it tell us? That for any x and y, if I have f of x, which is this, plus f star of y, which is this thing is bigger than or equal to x transpose y. It's a pretty non-trivial inequality, right? It's a pretty non-trivial inequality. In fact, I haven't really seen this. Maybe you can prove this in first principles, but I haven't seen this in really many other contexts than conjugates. And it also, remember, Fenchel's inequality was like, we proved that in one line. That was super easy to prove. And this derivation of conjugates was very easy. So it's like duality, right? Once you know conjugate functions, you can kind of do surprisingly powerful things. So for an indicator function, how about for an indicator function? The conjugate is just the maximum over all x of y transpose x minus the indicator function. Right? That's how we define a conjugate. But if I subtract off the indicator function, that thing's going to either be 0 or negative infinity. Right? It's going to either add a 0 or a negative infinity to the criterion, depending on whether x is in the set or not. So it's really the same thing as just doing constrained maximization. Maximize over all x in the set of y transpose x. So this is the indicator function of a set C. And this is that's its conjugate. We write that as I star of C, and we call it the support function. Okay, it's the support function of of the set C. And the last guy, and this is something I think, unless I had it in the slides, I don't have it in the slides. I'm pretty sure you'll prove this one in the homework. Is the conjugate of a norm. And for that argument, actually, you'll use things similar to what we did here. There'll be some steps where you consider kind of two cases, in fact, very analogous to these, to derive the conjugate. But if you give me an arbitrary norm, then its conjugate is the indicator function of its dual norm unit ball. So, for example, if this is the L1 norm, then the conjugate of the L1 norm is the indicator of the set of all points that have infinity norm less than or equal to 1. All right, I take its dual norm. I look at the unit ball in the dual norm, which means all the points that have dual norm less than or equal to 1, and that defines my set, and I'm the indicator of that set. That's what the conjugate function is. Okay. So let me ask you a question now that we've learned a few things about conjugates. What is the, for example, what is the conjugate of this? What does it kind of have to be? The conjugate of the indicator function of the dual norm unit ball. It's the norm, right? And so if I told you, for example, that for the L1 norm, its conjugate function was the infinity norm unit ball, what would the conjugate of the L infinity norm be? It has to be the L1 norm unit ball, right? And that actually you could show without even invoking this property. Okay, this property. You could actually just show that using these last two properties together. Okay, so the dual of the support function is going to have to be the indicator function again, right? For these reasons. So these two properties together will kind of give you a bunch of properties that may have seemed intuitively obvious, but it's a way to verify things. Okay, I think my watch is off. I have 1:15, but I think it's later than that. I mean 2:15, yeah, 2:22. Okay, let's take a break now, and then we'll come back and do the lasso dual as kind of our bigger example when we get back. Common. I mean, one of the first things you do when you learn SVMs, I think, is you talk about the SVM dual. At least that's, I think, it's a good perspective to understand the SVM problem. The lasso dual is not maybe as common because transparently, when you look at it, right, for the first time, it's not obvious what you would do because there's no constraints here. So the lasso problem, remember, we're given, say, a vector of continuous responses and then a matrix of predictors. And we're gonna find the parameters, regression parameters beta, that minimize this squared error between y and x beta times a half plus lambda times the L1 norm of beta. It's the Lasso problem. What's the dual function of this problem? Well, first, what's the Lagrangian? The Lagrangian here is actually just equal to the criterion. There are no dual variables, right? So for the Lasso problem, right, let's call this the criterion. Now our optimization variable is beta with regression parameters. The Lagrangian here is actually just the criterion, because usually we'd add, dual variables times constraints, but we don't have constraints, so it's just the criterion. So what's the dual function? If I want to minimize overall beta, the Lagrangian, just get f star. It's a constant, it's trivial. So the primal dual relationship is like not really very useful here, right? Of course, this lower bound's f star everywhere. It is equal to f star. So we didn't get anywhere. So one thing that is a common trick is to introduce constraints. Okay, and hopefully we'll have a few minutes at the end when I can kind of tell you that it matters how you introduce constraints, because each time you introduce constraints in a different way, it generally leads to a different dual problem. Okay, so there's not just one dual problem you can derive for any given primal problem, because if you manipulate it by adding constraints, that could lead to a different dual. Of course, they all have to be equivalent in some sense under strong duality, right? Because we know that each one of them must have a maximum criterion value that equals f star. But they could be easier or harder to derive or easier or harder to solve. So I'm going to actually make this substitution. Okay, I'm going to substitute in for x beta a new variable called z. And I'll rewrite the Lasso problem in the following form. Minimize over beta and z. Now I have two blocks of primal variables. Y minus z, a norm squared times a half plus lambda times the L1 norm of beta, subject to z being equal to x beta. So I haven't changed the problem at all. It's kind of a trivial introduction of an auxiliary variable z. But now that we have an equality constraint, we can work with the Lagrangian. Okay, we can actually derive a dual. So the dual function g of u, right, where I've introduced the dual variable for this block of equality constraints, is just defined by minimizing the Lagrangian over all my primal variables. So this is Lagrangian, the criterion plus u transpose z minus x beta. Minimize this over all the primal variables. And we can actually split that up into two minimizations. It's often the way that this works when we introduce variables. At least we usually try to make it so that we can split up the minimization of the Lagrangian into separate pieces. So I have, let me collect all the terms that, I'll just write down actually the original form first. And then we'll collect the terms that depend on z and depend on beta. So this is the same thing as, say, minimizing out over z, all the terms that depend on z. And adding to that, right, the minimum over all terms that depend on beta, right? Because I can split this up into these two minimizations, which is just lambda times beta minus u transpose x beta. Okay, so that's our task. To find the dual function is to minimize these two pieces. They're actually both fairly straightforward. So how about this guy? This is just a quadratic in z, our favorite thing. And the minimizer, okay, is going to be minus b over 2a. But b here is actually, it's u minus y, because I have a linear term here, u transpose z, and this is going to give me minus y transpose z. So the minimizer, it's called z star, is equal to minus b over 2a, but the quadratic here is identity, and I have a half, so it's really just minus b, and therefore it's it should be y minus u. Okay, so that's, you can verify that by also differentiating and setting equal to 0. Okay, and so if we plug that in, we get that the minimum over all z, that this thing is equal to we're going to get 1/2 times the norm of u squared plus u transpose y minus u. Is this going to give me what I have in the slides? Oh, wait. Must have made a mistake possibly here. This is what we get from taking the gradient set and equal to 0. So z is equal to y minus u. That's right. Okay, I guess it's probably equivalent to what I have on the slides, but just written in a slightly different form. Yeah, in fact, we can combine these terms, right? Because this is going to be the same thing as minus 1/2 y minus u squared plus whatever we didn't have. Just maybe what I have in the slides. I guess that's having the slides, yeah. Okay, I just combined these two terms to have a quadratic in u, to collapse these. Okay, and this is not going to end up mattering because this is just a constant, right? Okay, so that was minimizing out over this piece. How about over this piece? So for this guy, we're going to rewrite it first as a max because, of course, we usually want to deal with minimums, but this is going to actually be the conjugate function of something that we recognize. So we're going to write it as a max. So we're going to have to put a negative sign in front. And I'm going to also pull out lambda. Okay, it's going to be negative lambda times the max over all beta of u transpose x over lambda times beta minus the L1 norm of beta. So what is that? What is that right there? Forget about the minus lambda. What's that max? The conjugate of what function? The one norm, evaluated at what point? Right, x transpose u by lambda, because actually it's this thing transpose beta. So this is equal to minus lambda times the conjugate of the one norm evaluated at x transpose u over lambda. But the conjugate of the one norm is the indicator that this thing has norm less than or equal to 1. This is the indicator that x has L infinity norm less than or equal to 1. So I've used the fact that the conjugate of the one norm is the infinity norm, and is the indicator of the infinity norm unit ball, and I've evaluated at whatever point this is. Right, this is the argument to the conjugate function. In other words, it's minus lambda times the indicator that x transpose u and the infinity norm is less than or equal to lambda. Okay, so that's my dual function. It's a function of u alone, right? That's something that we should check, otherwise we made a goof somewhere. It's a function of u alone. And now we can think about this as actually defining a constraint, right? Because we're adding an indicator to and it's either 0 when this is met, or it contributes negative infinity when this is not met. So the dual problem is to maximize this, which is going to introduce a constraint on u, that's true. Okay, so the dual problem is to maximize just this piece, 1/2 the norm of y squared minus the norm of y minus u squared, subject to the infinity norm of x transpose u being less than or equal to lambda. Equivalently, we can actually get rid of this, right? Because this doesn't depend on u, this piece here, and we can flip the negative sign, get rid of this and call this a minimization problem, and say that this is an equivalent dual. This is equivalent to the dual. Okay, but oftentimes I'll just call this the dual. I won't even kind of worry about that. So Slater's condition holds, right? Because we have to apply Slater's condition to this problem. This was the one in which we were taking, this is the one whose dual we took. So this is convex, and it's strictly feasible. There are no inequalities, so Slater's condition holds, which means that the optimal value of this problem is the same as the optimal value of this top problem, and we have strong duality. It's not equal to the optimal value of this problem, though. Okay, so that's an important thing to remember. If you actually took your dual and you modified it so it was more familiar to you, and then you checked the duality gap, if you looked at the difference between the optimal criterion value of the primal and this, you don't know that that relationship is, that's not the one you're looking for, right? You're looking for this when you're actually computing the duality gap. Although, of course, this is equivalent to that problem in terms of the solution. Okay, that was what I said here. But note, the optimal value of this last problem is not the same as the optimal value of the lasso problem. And the final thing, which is important to note, is that given a dual solution, any lasso solution, beta must satisfy this. We can actually find the lasso fit, x beta, right? The predictions. This is what we predict for y. This is the linear combinations of the variables just by taking y minus u. So that comes from the stationarity condition for z. Okay, so look what we did here to derive the dual. Okay, so because strong duality holds, this implies that the primal solutions, let's call them beta star and z star. This is the lasso coefficients, and this is the lasso fit, right? Because z at optimality has to be equal to x beta. These must minimize L of beta z at u star. So once you give me the dual solution, I can think about minimizing Lagrangian over all beta z to characterize the primal solution. Right, but carrying out this exercise of figuring out, given u, which z and beta minimize Lagrangian, we've already done that to drive the dual. So let's just look back. Given u, the best value of z, the value of z that makes this as small as possible is just y minus u. Okay, but at optimality, this is just x beta star, right? Because that was kind of our trivial constraint that we introduced. So that's the relationship between the primal and dual solutions. So once you know the dual solution, you just take y minus u, and it gives you the predictions, lasso predictions. Okay. There's some relationship between the primal and the dual here that's nice, and I think I'm going to skip just because we don't have much time. But it turns out this is an example in which this problem is easier to study mathematically in many ways than the lasso problem. Okay, because this thing, the dual problem involves projecting y onto a convex set. I'm finding the closest u among all u that satisfy this. That's a convex set. In fact, it's a convex polyhedron, right? This is just the intersection of a bunch of half spaces. I'm taking x, say j, the jth column transpose u, and I haven't said that's between lambda and minus lambda, or between minus lambda and lambda. So this is just a convex polyhedron. So the dual solution is characterized by projecting y onto that convex polyhedron. And the primal fit, x beta, the lasso fit, is just the residual from that projection. Right? It's y minus the projected point. So there's some nice kind of geometry that goes along with this that allows you to maybe make statements about the lasso problem that otherwise would be difficult to say directly from this criterion. Okay, and if you're curious, you can come to my office hours and I can tell you more about that. But that's what this picture was supposed to convey, this kind of crazy looking picture. Okay, let's move on because we actually do have a few more good things to cover. And we only have, looks like 10 minutes. So this is the extremely kind of important relationship between conjugates and dual problems. And we've used it already, actually, when we derived the lasso dual. And we used it already when we derived the dual of the problem in the very first example. But here's what it is explicitly. Let's suppose you want to minimize f of x plus g of x. That's my problem. So because it doesn't have constraints, right, to derive its dual, I'm going to do something like this. Minimize f of x plus g of z subject to x equals z. It's the trick we used in the lasso problem. The Lagrange dual function is just gotten by taking this and adding u transpose z minus x, right? And now let's just attribute basically minus u transpose x to f of x and u transpose z to g of z, and think about two separate minimizations. Right, we're minimizing f of x minus u transpose x, and we're minimizing g of z plus u transpose z. That gives us actually just this. So why is that the case? Well, here I've just rewritten the definition of a conjugate function, right? It used to be defined in terms of a max. I just took the negative of both sides and then changed the max into a min. So the negative conjugate of f at the point u is defined as the minimum over all x of f of x minus u transpose x. It's equivalent, of course, to our definition. So here we're minimizing f of x minus u transpose x. So that's the negative conjugate of f at u. And we're minimizing g of z plus u transpose z. So that's the negative conjugate of g at minus u. So in other words, the dual of this is this. It's completely generic. Applies to any two functions, right? So if you have now, for example, a problem that involves the one norm and some loss function, you can think about what's the conjugate of my loss function? It appears here. What's the conjugate of the one norm? It's going to be an indicator, right? That this thing has infinity norm less than or equal to 1. Or whatever kind of pieces you have. You can think about it breaking down this way. This is, I think, just a very useful thing to remember, that these two are duals. Okay, I'll probably save you some time in deriving duals in the future. So some examples of this last calculation. I guess I've already said this one. Or no, I didn't say this one, sorry. The dual of f of x plus an indicator function is the negative conjugate of f at u minus the support function at minus u. And the flip side of that is actually what happens when you have a norm, right? In which case, a support function, the norm you can always think of as a support function because it's the maximum over all points that have, infinity norm less than or equal to 1 of the inner product of that with x. So it really is a support function. The flip side of this is that the dual of this problem is this guy, right? I have to take the conjugate of this, which gives me the negative conjugate of this, which gives me the indicator that u has dual norm less than or equal to 1, and take the negative conjugate of f at u. Okay, so it's just some nice forms to remember in general. Something else very special about dual problems, which we saw happen in the case of the lasso problem, is that by taking duals, we can shift a linear transformation from one piece of the objective to another. And this is a very general principle that people use all the time. I use all the time when I'm thinking about solving problems. In a case in which one of my two, say, functions in the criterion, or one of many functions in the criterion, has a linear transformation in it, and that's making the minimization difficult. By taking duals, you can actually shift the appearance of that linear transformation to somewhere else. This happened in the lasso problem. Let's go back to that. Okay, I had a linear transformation in the squared error term. In the dual problem, that got shifted to appear in the conjugate of the norm. Okay, I got an x transpose in the infinity norm constraint. Okay, and likewise, if I had a linear transformation in the one norm, I could shift it to be in the dual criterion with an appropriate, by setting up the problem appropriately. Okay, so here's what this looks like in general. Suppose I have f of x plus g of a of x, where a is just some linear transformation, some matrix. So I can equivalently set this up as minimize f of x plus g of z subject to ax equals z, right? And as before, okay, if we go through this exact same calculation that we did to get this one, okay, you can fill out the details on your own. You're going to get that the dual is to maximize overall u, the negative conjugate of f at a transpose u minus the conjugate of g at minus u. So the linear transformation has gone from basically being composed with g to composed with the conjugate of f in the dual. So I gave another example here, right, where we can take the linear transformation out of a norm, if that's difficult somehow to deal with, and put it into, this should say f star, I'm sorry, f star of a transpose u. Okay, where am I with time? I keep having to close and open because my watch is broken. Can somebody wave your hands when it's 2:50? Because I won't be able to tell. So let's talk about cones. Let's see what I want to talk about the most. actually, maybe, you think I'm going to skip talking about cones and cone problems, because I don't think that appears in your homework, and that's not somehow very crucial, I think, to learning duality. It's a nice thing to learn, and Javier's going to come back and cover STP and conic duality in more detail when he teaches second order methods. So I might skip this. And if we have some extra time in a future lecture, I guess Javier might come back to this, or he might do his own treatment of it. But there's a very nice kind of just general story of duality and conic problems. I'll just give you the punchline, okay? That if you ever have a conic problem of this form, minimize a function f of x subject to ax lying in a cone. Remember we said this is a very, very general problem form. We can think of like this basically as being, in some sense, if we add, in some sense this is one of the most general problem forms we can consider. The dual of this problem is via kind of that same argument that we used a couple slides ago, and a new kind of concept, which is the dual cone, is just to maximize over all u the negative conjugate of A transpose u subject to u being in the dual cone. So see why this is so useful, and why this is something that's used by tons of solvers like CVX and a lot of kind of generic convex solvers, is that sometimes it's very difficult to deal with a linear transformation of a variable being in the cone. So we can shift that over to the criterion, right? So now this appears in the conjugate of f, and we get u being in the dual cone. So no linear transformation appears here anymore. Now it may be easier somehow to project onto this or to deal with this constraint via like an interior point method or something. This is a very common trick that these general optimization solvers use. Okay, I just didn't tell you what the dual cone is, but the definition is just a couple slides back. And for example, the PSD cone is self-dual. So if this was a PSD constraint, this would again be a PSD constraint. So what I wanted to get to is this stuff, because there's a couple subtleties I wanted to mention. I've kind of already mentioned them, but make them explicit. Oftentimes we're going to transform the dual into an equivalent problem and still call this the dual. And under strong duality, that's not going to matter, because all we really care about in some sense is the solution to the dual. And then we're going to use that to characterize the solution to the primal. So by transforming the criterion, we won't kind of have changed the solution to the dual. But you cannot use that in order to measure the duality gap. That'll just give you problems if you try to use that as an algorithmic stopping criterion. Another thing is that there's different ways to derive duals for unconstrained problems. So if we go back to this Lasso problem, think about, you can do it on your own time, think about what happens if you actually substitute z for beta in this term. So instead of this equivalent problem, I wrote down another problem, which is y minus x beta norm squared times a half plus lambda times the L infin norm of z subject to z equals beta. That's also an equivalent problem, right? I can substitute in this guy for z, and then pose the equality constraint that z must equal beta. That's going to give me a different dual than this one here. And in fact, it's going to be, in many senses, less desirable. It's harder to work with, because it involves x transpose x inverse. So computationally, we don't really want to look at it, because it involves inverting a matrix, and also there's trouble in even kind of stating what it is when x transpose x is not invertible. But that thing, you could still somehow state that dual in a general form. It's just complicated, and it's equivalent to this. It's just not as useful. So if you have a problem that's unconstrained, think about all the various ways you could kind of derive duals. It's often helpful to look at all of them. One of them may be more useful than another. OK. And my last kind of general tip is just to, whatever you're doing, derive the dual if you can. Because even if it's not somehow more useful to solve, it's often, I think, provides an interesting complementary perspective to your problem. So one of the very first things I do when people are having trouble understanding or solving an optimization problem is ask them what the dual is. And their answer is often, I don't know, I've never thought about it. But to me, that's almost always the first step. If you can derive the dual, take a look at it, and you kind of may learn something from it, or it may be actually easier to solve. And we'll finish with just something that I think is kind of neat, and it goes full circle, and it's the same property as, in some sense, it's very similar to the properties of the dual norm being the primal, and the conjugate of the function being the function. And it's this concept of taking the dual twice. So we saw that I claimed that for LPs you could check this. Taking the dual of the dual LP is the original LP. And you can also check that for QPs, and you can actually do this kind of check for various problem forms. But you don't need to in a sense because this fact is true in general, in a very general setting. And okay, so here I have you check it for linear equality and linear equality constraints for an arbitrary function. We go through the argument here. But I'm just stating here that actually this is true well beyond kind of those special cases. Essentially, for any convex problem, that's going to be the case, as long as the convex functions are closed. Which again, I said it's somehow you can think of it as being always the case. It would be very odd to have convex functions that weren't closed. This just means that their sublevel sets are all closed, or that they're continuous if their domain is all of Rn. Okay, so proving this is actually quite involved, that the dual of the dual is the primal in general. But Rockefeller does it in his book, so if you're curious to see how that's done, you can take a look at chapters 29 and 30. Okay, so I think that was all of it, and I'm a little bit over time. So yeah, I'll see you guys on Monday for the little test.